Yes, good morning to my dear friends, and also welcome to electronics online classes. Look here, in the previous class, we are discussing about the feedback amplifiers, and in that feedback amplifiers, we have completed the 50% of topics, means syllabus, because as I said to people, it is very small topic, and also it is carries only 5 marks. That's why the topic is very small and simple. And today is going for the lecture number 4. The lecture number 4. Look here, in the previous class we are discussing about what is the effect of the negative feedback on the gain. You have done the derivation, the voltage gain of an series voltage negative feedback amplifier. It means if you apply the negative feedback on the any amplifier, how the gain will be reduces. And also you studied about how actually the gain is stable, how the gain is stable and how the gain reduces. And as we know already, you have done the derivation. By the derivation, you have proved the gain, the voltage gain, that depends only on beta. That depends only on beta. And you know beta nothing but the feedback factor, or it is nothing but feedback ratio. And this also, you know, the feedback network that consists of only the passive components. It may be resistor, it may be capacitor, it may be inductor. And because of your gain, that depends only on the feedback factor. And that feedback network is constructed by using only the passive components. But the important thing, the passive components does not depend upon your aging effect or changes in the supply voltages. As we know, if you construct the feedback network by using your active elements, it may be transistor, it may be FET, then you are having variation in the voltage gain, because that is because of temperature, that is because of your aging effect, that is because of your supply voltage. But that is not there in your, if you construct the feedback network by using the passive elements. And also you have done, if you apply the negative feedback, you have done the small derivation, you have proved mathematically, if you apply the negative feedback on amplifier, what happens? There are very small changes in the gain. Without applying the feedback, there are so many variation in the gain. But if you apply the feedback, you are having very small variation in the gain. It means we can say about the gain is stable. You are not having any variation in the gain. We are having very small variation. That variation you are not considering that. In general, you are saying about the, if you apply the negative feedback on amplifiers, what is it? You get the stability in the gain. And also you studied in the last class about different types of topologies or different types of negative feedback connections. It may be voltage series, or it may be voltage shunt, or it may be current series, or it may be current shunt. In this 4 different negative feedback topologies, we are giving more importance to the voltage series feedback network, voltage series feedback topology or connection. Why we are giving more importance to the voltage series feedback topology? Because as I said, it will give the more input impedance and it will give the very less output impedance. If you use the voltage series feedback network, what I said, we can increase the input impedance, also we can decrease the output impedance. and how it is possible to increase the input impedance and decrease the output impedance. Today we go for that. And also another important parameter of negative feedback. The most important thing in the parameter, what are the advantages of negative feedback. When you are done in the yesterday's class about the derivation, how the voltage gain will be stable. Stability in the voltage gain, you have done that derivation in the last class. And now today we will go for the what is the effect of the negative feedback on input impedance. As I said here, if you apply the negative feedback on amplifiers, you can increase the input impedance. And this I said theoretically, orally, but you go for that derivation. You go for the proof for that. What I was saying, if I said in the orally it is not correct, that I have to show by you want that proof. That proof you go for today's class. And also another important thing in your negative feedback, it will decrease output impedance. How to decrease output impedance, that also go for the small derivation. And remaining last, that is nothing but the frequency response. As I said already, if you apply the negative feedback on any amplifier, we can increase the frequency response, and also the bandwidth increases. How it is possible to increase the bandwidth, and what is the effect of the negative feedback on frequency response? We will go for in detail about the proof. I said in general about advantages, and as I said, why we prefer negative feedback? The one thing important, we can control the voltage gain. Also, you can control the input impedance, output impedance, and bandwidth. As I said, in general, it is not possible to control the voltage gain, input impedance, output impedance, and bandwidth without applying the feedback. If we apply the feedback, we can control all the parameters. That is the most important advantage of your feedback. Why we prefer feedback? Because, as I said already, to control the other parameters, and also, as I said, to reduce the noise and produce the distortion. Now we will go for the today's class about expression for input impedance. Or I can say about how we were, what is the effect of the negative feedback on input impedance. And once again, we are using the voltage series feedback topology. And another important thing, why we want more input impedance? Why we want more input impedance? In general, in amplifiers, we want more input impedance. Why we want more input impedance? If the input impedance is very more, it does not affect the preceding stages. It does not affect the preceding stages, or it does not affect the voltage or current source. If your input impedance is very more, that does not affect the preceding stages, or it does not affect your current or voltage source. That's why we prefer the more input impedance. And we will go for that. First, you draw the need diagram. And as I said to people, we go for the, you are using the voltage series feedback topology. Once you draw that block diagram, you are already perfect. In the last class, you studied about amplifier with gain, and here you are using a feedback network, and you are using the voltage series. Here, voltage series, and as we know, the voltage series is nothing but in the output. Here it will be the feedback network, say about beta. And here you are using RL. This may be your RL. This is your input. And as we know, always you are measuring the. Yes, you are measuring the. This is your voltage by connecting in parallel. And here also we want your series means you are adding or subtracting the voltages in series. And here also you are using voltage source, and this is nothing but your VS. This is nothing but your VL. This is as you studied in the last class about here. This is the block diagram of your voltage series feedback topology. Now we go for the derivation for the input impedance. We go for the derivation for input impedance. And as I said to you people, first you have to write what is the input impedance. In general, input impedance. As we know, the in general input impedance, we know that yes, input impedance ZI equal to ZI equal to VI. Z nothing but resistance VI by II. Equation number 1. Consider the input impedance. Yes, the input impedance is nothing but the input voltage to input current. That is without feedback. In general, input impedance. Now use your with feedback. With feedback, in place of VI, you can write VS. VS by II. This is equation number 2. And also, how you have done the yesterday's class, here also go for the same, you are using the same formulas. Once again, use your beta, your feedback factor, that is nothing but VF by V0. Or you can write about VF equal to beta into V0. Now you consider you are using the negative feedback. If you are using negative feedback, what happens with the negative feedback? In the amplifier, if you are using negative feedback, then what about the input voltage? The input voltage VI equal to Vs minus Vm. As you know, the standard equation. Because while applying the negative feedback, they will reduce the input voltage. Then Vi as it is, this Vs as it is. Now in place of Vf, we can write about beta and V0. We can write about beta into V0. Yes, we can write about beta into beta. And also, I can write another otherwise not necessary. But Vi as it is. And here Vs as it is. Now beta as it is. In place of V0, we can write, since the here we can write A is equal to V0 by Vi. We can write about A into Vi. A into Vi. V0 is equal to A into Vi. Then you take Vi this side and Vs this side. That becomes Vs equal to, yes, you take Vi plus A beta into Vi. Then you take Vi common, Vs equal to Vi 1 plus A. Yes. Now it may be the equation number 3, it may be equation number 4. Now substitute the equation 4 in equation 2 because we want the input impedance with feedback. That is nothing but ZIF equal to, yes, in place of Vs we can write about, in place of this Vs we can write Vi into 1 plus A beta, right? Vi into 1 plus A, right? 1 plus divided by II as it is, right? II as it is. And as we know that Vi by II, nothing but that is ZIF. ZIF equal to ZIF into 1 plus A. This is nothing but your input impedance. Very simple. As I said here, if you are using negative feedback, especially you are considering the voltage series topology, what happens? The input impedance increases. The how much the input increases, that is 1 plus A beta times. If you are using the negative feedback on any amplifier and if you are using the voltage series feedback, then what happens? The input impedance increases by 1 plus A beta times. As I said already, if you are using the negative feedback in any amplifier, you can increase the input impedance. And how much you can increase input impedance? That is nothing but 1 plus A beta times. We can increase input impedance by 1 plus A beta times. This is the simple proof about your how actually mathematically prove what I said about if you use the negative feedback on amplifier, they will increase the input impedance. Very simple. As we know, the voltage series feedback topology, the first you draw the diagram, then we are having the basic knowledge about we know that input impedance is nothing but Vi by II, that is without feedback, and with feedback that is Vs by Vi, and also we know about beta, that is feedback voltage to output voltage, and also we know about gain without feedback, that is V0 by Vi, and here we want Vf and beta and V0, and if you use the negative feedback in amplifier, what happens? The input voltage decreases, the input voltage decreases, that is Vs minus Vf, Vi as it is, Vs as it is. In place of Vf, we can write about beta and V0. You write about beta and V0. And also in place of this V0, we can write A into Vi. Here you can write about A into Vi. Here V0 equal to A into Vi. Yes, you written about Vs as it is, Vi as it is, in place beta as it is, in place of V0, you can write A into Vi. Remaining, you take this, you take Vi, take one side, and Vs you take another one side. Then it becomes Vs is equal to Vi plus A beta into Vi. Here you take common, Vi, you take a common, that becomes 1 plus A beta into Vs. And actually we want this Vs to substitute in the equation number 2 because you are finding the input impedance with feedback. Then it becomes ZIF is equal to Vi 1 plus A beta. This is the value of I can write about 17 here. ZIF is equal to Vs, not necessarily Vs by sorry, not necessarily. This Vs you can consider here, and II as it is. Then Vi by II nothing but ZI, and it is 1 plus A beta. It means if you are using the negative feedback in amplifier, we can increase the input impedance, that is 1 plus A beta times. This is about a simple derivation of your input impedance. How actually the input impedance increases if you use the negative feedback in any amplifier. And I will go for another small derivation. they'll ask in 3 months about the derivations, because as I said already, they'll ask in this chapter 5 marks. In that 5 marks, they'll ask 1 3 mark question, and also they'll ask 1 2 mark question. That is also they'll ask one simple problem. Now we go for the expression for output impedance. We go for the expression for output impedance. We go for the output impedance. Expression for output impedance. It is also called the cutout. Now we are using same voltage series feedback with a small correction. Look here, whenever it is not simple how you have done the input impedance. While finding the output impedance in your amplifiers or in amplifier if you are in negative feedback, how to find out the output impedance? You have done the 2 conditions input. The first condition, whenever you are finding output impedance, make it the input voltage short. The first condition, the input voltage, the input source or voltage source, the input voltage source Vs is 0, or you can make it short circuit. Make it short circuit. You can apply the 2 conditions. While going for the derivation of output impedance, you have to go further. You have to verify the 2 conditions. One condition, the voltage source is 0 or make it short circuit. Why to make it the voltage short circuit? Short circuit. If you apply the voltage source, they may affect your output impedance. You are not getting the desired output impedance. That's why make it the voltage source as short circuit or 0. And second one, remove RL. Remove RL or make it RL equal to infinity. And in the output we can use the hypothetical source. We can use the in the output you can use the hypothetical source. And this is about the 2 conditions of output impedance. Now by using these 2 conditions, once again we will draw the same voltage series feedback topology. Look here once again you are using an this is your chart knot. It's A into A. A into A. And here I assume nothing but line up. Yes, here we are using the hypothetical voltage source. That is your V0. Now, as it is similarly, it is your amplifier with the gain A. And once again, you are using a feedback network. You are using a feedback network, that is here remaining is similar as you are using this is nothing but the beta or the feedback network, that is your beta. In the input it is the same, but only thing is make it the short circuit the Vs. The Vs is 0. So 0. Important change. Here we got the This is about the diagram of your voltage series feedback topology while going for the expression for the output impedance. Say once again we know already, we know that yes, how to find the output impedance, that is nothing but Z2 Z not equal to yes the V naught by V naught by I naught. And for this actually this is nothing but your output impedance, output voltage to output current, equation 1. And while going for the derivation in the output section, you have to apply the KVL. Apply the KVL for the output section. In the second step, apply KVL for the output section. Apply the KVL for the output section. Yes, the V naught equal to I naught to Z naught plus A into VI. Can write about the Z naught. Can write about yes, V naught equal to I naught to Z naught. I naught into Z naught plus AVI. And write about AVI. Right. Then, as we know already, in your amplifier, you are finding the output impedance, and also you are using negative feedback. If you use negative feedback in any amplifier, what happens? The input voltage, that is VI equal to Vs minus Vf. This is equation number 2. Because as we know, if you apply the negative feedback in amplifier, what happens? The input voltage decreases. And here, as we know, the basic condition, the Vs is 0, because the Vs is short circuit. Can write about Vs is 0. Then it becomes Vi equal to minus Vf. That becomes minus Vf. This Vi you have to substitute in the equation number here. In the equation all the this will be your 4. Substitute equation 4 in equation 2. Substitute equation 4 in equation 2. You can write the V naught equal to is I naught into Z naught plus A as it is. In place of A, correct Vf minus A into Vf. Right. Any doubts? Then in place of the Vf, we can write about, as we know, Vf equal to beta into V naught. According to our yes, the alternate beta equal to Vf by V naught. Or you can write Vf equal to beta into V naught. Not necessary. You know already basic idea. Then in place of Vf, we can write beta and V naught. Here I write once again. The V naught equal to I naught plus Z naught minus A. In place of Vf, we can beta into V naught. Can write beta into V naught. Beta into V naught. Yes. Very simple. I naught Z naught as it is. In place of this Vi, you can A as it is. In place of Vi, you can write minus Vf, because Vi is equal to minus Vf. And this Vf, you can write beta into V naught. Same thing, because you want to write it's not necessary. If you want to write beta VF by V naught, and we want this VF beta and V naught. Then you take the V naught one side and Z naught and I naught Z naught one side. Or you write about V naught plus A beta into V naught equal to I naught into Z naught. Beta. Then here you take V naught common. We take V naught common. That becomes 1 plus A. This is equal to I naught by beta. Then you want this I naught to divide here. This 1 plus A beta divides here. We want ZOF. ZOF is equal to the output impedance with feedback. That becomes this I naught come this side, or you can write otherwise. V naught by I naught equal to Z naught by 1 plus A. And finally you can write this V naught by I naught number. Yes, you are doing here ZIF. And write about Z2F equal to Z naught by 1 plus A beta. See nothing but your output impedance. Very simple. And expression for output impedance, and only, like I said, we have to follow the two conditions. First condition, make it the VS, the voltage should make it short circuit, and then you have to use the make it RL, remove the RL or make it RL infinite, and you can use the high power electrical source here. That way becomes gain, and also use your as we know, first step, the output impedance, that is the limit ratio of output voltage to output current, and apply the KVL per output section. Here we want this output voltage, that is nothing but I naught to Z naught, I naught to Z naught plus AVI plus this AVI. Once again repeat, apply the KVL for the output section. V naught equal to I naught to Z naught plus AVI. I naught to Z naught plus AVI. Then, as we know, if you apply the negative feedback in amplifier, what happens? The input voltage decreases. That's why Vi is equal to Vs minus Vf. And as we know, here in your output impedance, when you are finding output impedance, the Vs is 0. The Vs is 0. That's why Vi is equal to minus Vf as it is. Then you take same equation, V naught equal to I naught Z naught, V naught I naught Z naught, but in place of Vi, you can write about Vf. In place of the Vi, you can write about Vf. And as we know how to find Vf, that is from the beta. As we know the feedback factor, the feedback voltage to output voltage, we want is Vf, that beta into V naught. This Vf, we can, in place of Vf, you can write beta into V naught. As it is same, the V naught as it is, this I naught Z naught as it is, and here minus as it is A beta into V naught. In place of Vf, we can write beta into V naught. Then you take same side one side, same terms one side, and here V naught you take this side, it will be plus. Here also V naught is there, and this I naught Z naught as it is. Then you take the V naught common here, you take V naught common, then it becomes 1 plus A beta, this becomes Z naught as it is, and this V naught by I naught, this we will divide here, Z naught by 1 plus A beta. It becomes V naught by I naught nothing but ZOF, that is the number of output impedance, and this Z naught, that is 1 plus A beta. The important thing in this derivation is about if you use the negative feedback in amplifiers, then what happens? the output impedance decreases by 1 plus A beta times. The most important thing, what we want in general, we want very less output impedance, or we want the output, if we apply the negative feedback, they will reduce the output impedance. And how much they will reduce the output impedance? That is 1 plus A beta times. It means in general, if you are using the negative feedback in amplifiers, we can reduce the output impedance, that is 1 plus A beta times. We can reduce the 1 plus output impedance, that is 1 plus A beta times. It means if you are using the negative feedback in amplifier, you can reduce the output impedance, that is 1 plus A beta times. This is about in simple proof about the how actually the output impedance reduces. And let me ask the question, why you want very less output impedance? Why you want very less output impedance? Look here, if you want, if you are having more output impedance, you are having the more losses. We want to reduce the losses, and also we have to deliver the voltage or power to the load with the minimum losses. That is done by using your negative feedback. Or whenever the output impedance is very less, then only can transfer the voltage or power to the load with the minimum losses. If you are having the more output impedance, you are having the more losses. The signal is not passing more to the load. That's why we prefer the output impedance very less, then only can transfer the voltage or current or power maximum to the load. That is about the output impedance, how actually the output impedance decreases if you use the negative feedback in the amplifier. This is about the in simple way of what is the effect of the negative feedback on input impedance and output impedance. As you have done the derivation, only simple you have used the voltage series feedback topology, and if you use the negative feedback in amplifiers, we can increase input impedance, that is 1 plus A beta times. In the same way, if you use the negative feedback in amplifiers, you can reduce the output impedance, that is 1 plus A beta times. And last we go for the what is the effect of bandwidth and what is the effect of frequency response with the feedback. Because you know about voltage gain, we know about input impedance, we know about output impedance. Now finally go for the frequency response. What is the effect of frequency response? Very simple, not necessary. Only you can change the small change in the diagram, make VS short circuit, and can use the high point of the source at the output. You can remove all powers also. V0, and also you can be, this is very simple. We know about the basic knowledge, the output impedance and the output voltage, output current, and apply KVL for the output section. V0 equal to I0 in Z0 plus EBI, and as we are using negative feedback, Vi is equal to Vs minus Vf, you know already. And here the Vs is 0 because you have done the short circuit in the input. That becomes Vi equal to minus Vf. And this V0, I0 Z as it is, in place of this Vi, we can write about Vf, and in place of Vi, I can write beta into V0, and remaining the very next one is, or next thing is very simplification. Just V0 as it is, I0 Z as it is, minus A beta V0, you take A beta, you take this side, and here you take common V0, and plus A beta, this I0 Z as it is, and here you take V0 this side, and it divides here. This one same will also divides. This is about the simple way of your output impedance. Yes, we will go finally. We will go further. What is the effect of the frequency response? We will go further. Frequency response of your negative. As I said already, if you use the negative feedback in amplifiers, we can improve the frequency response. The frequency response is very good. About frequency response. here, as you already were having some idea, you have studied about the frequency response for the C amplifier, also studied about frequency response of your RC coupled amplifier. In overall frequency response, nothing but it is a graphical representation of the frequency versus voltage gain. For different frequency, what is the voltage gain? That you are studying systematically. That is nothing but your frequency response. And as we know, if you apply the feedback, what is the effect of the bandwidth? Because in frequency response, we are giving more importance to the bandwidth. We are giving more importance to the bandwidth. And also in general, we want more bandwidth. Why you want more bandwidth? Because the range of frequencies, the gain should be constant. We want so much of range of frequency, the gain should be constant. And as for I'll give a small example. Now I am taking the class. This class helpful to so many students. Then it is good. Means I want more bandwidth. In what way I want more bandwidth? My class has to listen or hear by so many students. Then it is very good. The same way for amplifiers. We want more bandwidth. And if you are not using the feedback, the gain will be reduces. If you use the feedback, you can increase the gain. Sorry, you can increase the bandwidth. How to possible the increase the bandwidth? If you are using the negative feedback in amplifiers, it is possible to increase the bandwidth. How will go for that? As you know the frequency response curve. First you go for the without feedback. You go for the without feedback. And this is nothing but with feedback. You already started in your this is your frequency response. And here it will be F2 dash, sorry, F1 dash, and here maybe the this is the bandwidth. Here this is your AV maximum. This is AV into 7 times AV maximum. And this is the AV into 7 times. Look here. This is the without feedback, and this is with feedback. It means, as we know, without feedback, as we know, the gain is the bandwidth is very small. Because we are having very narrow bandwidth, and if you use the feedback, we are having the very more bandwidth. And as we know, the bandwidth is nothing but the F2 minus higher cutoff frequency minus lower cut off frequency. Bandwidth without feedback. With feedback, the bandwidth BW dash equal to F2 dash minus F1 dash. And when you get the more bandwidth, we want very high, higher cut off frequency and very less low cut off frequency. It means more F2 than the F1. Then only get more bandwidth. If you use the negative feedback in amplifiers, we will get the more bandwidth. How will we get more bandwidth? That is, we want the F2, can write F2 dash equal to 1 plus A beta times. The F2 dash is equal to 1 plus A beta times. The frequency increases. But F1 dash equal to 1 divided by 1 plus A beta times. Or to write F2 dash is equal from the F1 and F2 dash. The F2 will increases 1 plus A beta times and F1 will decreases 1 plus A beta times. That's why you get more bandwidth in your if you apply the negative feedback. And finally, you can go for small derivation. How we can increase the bandwidth? How we can increase the bandwidth? Yes, the important thing in general for amplifiers, the gain and bandwidth product should be constant. Gain and bandwidth product should be constant. In general, for all the amplifiers, the product of gain and bandwidth product will be constant. The product of gain and bandwidth will be constant. And also, as we know, the gain, even gain with feedback is equal to the gain A dash into BW dash. Also important thing, the gain and bandwidth product with the feedback, without feedback is equal to the gain and the bandwidth without feedback. This is nothing but without feedback. This is with feedback. You can write about without feedback. That is with feedback. Feedback. It means the gain and bandwidth product with feedback is equal to without feedback. The gain and bandwidth product without feedback is equal to the gain and bandwidth with feedback. This also can simply go for the small derivation. This A into bandwidth without feedback is equal to A dash into bandwidth. Now we take this term aside, A dash into bandwidth with feedback equal to A into BW bandwidth. Then we want this BW dash. This BW dash equal to A into BW. This A dash divided by A dash. And this, as we know, A dash equal to A divided by 1 plus A. In the voltage gain for amplifier, use that formula here. The bandwidth dash equal to A into beta bandwidth. A dash A divided by 1 plus A. Or if you want to write once again, it is not clear if you write in the below. What is the effect of the bandwidth? As we know, the bandwidth, right here, the bandwidth is F2 minus F1, that is without feedback. with feedback equal to F2 dash minus F1 dash. And also, as I said, the gain and bandwidth product should be constant. And as we know, the gain and bandwidth without feedback is equal to the gain and bandwidth with feedback. The gain and bandwidth product without feedback is equal to the gain and bandwidth with feedback. This also you can simplify. You take this from this side, A dash into B W dash. B W dash equal bandwidth. This will take this term A into bandwidth. Then you take this A this side, beta, this bandwidth with feedback as it is. That becomes A into bandwidth. This A divides here. And in place of A, you can write what you know A already. You know A already. That is A divided by 1 plus AB. 1 plus AB. This is up here. It becomes bandwidth dash is equal to A into bandwidth divided by E divided by 1 plus AB. Yes, this we can write once again. The bandwidth dash equal to A into bandwidth divided by A into 1 plus A. This A cancel. It becomes BW dash equal to bandwidth 1 plus A. This is about the small derivation. It means if we use the negative feedback in amplifiers, we can increase the bandwidth up to 1 plus A beta times. It means, as I said already, if you are not using the feedback in amplifiers, the bandwidth decreases. And if you use the negative feedback in amplifiers, you can increase the bandwidth. How much you can increase the bandwidth? That is 1 plus A beta times. The most important thing, as we know, this is so important for all amplifiers. If you are studying amplifiers, in the all amplifiers, the important thing, the gain and bandwidth product should be constant. The gain and bandwidth product should be constant. And also, as we know, the gain and bandwidth without feedback is equal to the gain and bandwidth with feedback. And as we know, we can simplify this. A dash into BW, A dash into what? With feedback, B double dash with feedback, A without feedback, B double without feedback. That is bandwidth, this is gain. Then we want this with feedback. We want the bandwidth with feedback. You A dash that divides here, this A into A nothing but voltage gain and B double bandwidth as it is, and you substitute A dash value, that is A divided 1 plus A beta, that we know about voltage gain negative feedback. And finally, you have to substitute that A into BW bandwidth as it is. In place of A dash, can write A divided 1 plus A beta, and it is simplify. We get about we can increase the bandwidth nearly about 1 plus A beta times. In the overall, what you confirm, what you will get the conclusion. Conclusion nothing but if you use the negative feedback in amplifiers, we can important thing we can make it stability in the game. That you have done in the stage class, how the gain is stable if you use the negative feedback. And second one, today I have done about if you use the negative feedback in amplifier, you can increase the input impedance. That is 1 plus A beta times. And third one, once again if you use the negative feedback in amplifiers, you can reduce the output impedance. That is 1 plus A beta times. And also, finally, we can increase the bandwidth. That also 1 plus A beta times if you use the negative feedback in amplifiers. This is about in simple way of the importance of negative feedback. And also I said it is so important for amplifiers because you are having so many advantages, And as I said, in general also I done that proof for that how actually the gain will be stable and how your input increases, how output increases, and what is the effect of bandwidth, and also what is the effect of bandwidth and gain product. This is about in today's class. In the next class, you go for the very small thing is that is about problems on this feedback networks. Thank you.
So chapter 8